I'm going to attempt to add bifenazate deuterated to our LCMS MS method. So the first thing that I'm going to do is run a product ion scan on the LCMS, and I know that the molecular weight of bifenazate is 305.4 grams per mole. So what I'll use as my precursor ion is going to be the mass of the analyte plus 1, because when the compound gets ionized, it adds a proton to the compound, so the mass should go up by 1 unit. So I'll look for a mass to charge ratio of 306.4, and then I'll do a product ion scan starting with that precursor ion at 306.4, and then we'll see what that looks like. And this bifenazate, it came in a 1 milligram sample size, so I diluted it in 2 mils, so I have 500 parts per million, and then I made a 1 part per million neat, and then a 0.15 part per million with a cannabis oil matrix, because this is going to be likely the concentration we'll use for the internal standard. And then the 1 part per million neat is just going to help me see the bifenazate a little more clearly with a stronger signal. So let's see. Okay, so I copied my method for our normal analysis into a new folder, and I'm going to delete all of these channels and make a new one for bifenazate. But for my bifenazate non-deuterated, I have a collision energy for these MRMs at 10 and 20. So for my product ion scan for bifenazate deuterated, I'm going to try a collision energy of 20 and just see what that gives me. And then we can go from there to see, we'll do a collision energy, sort of like a scan across a bunch of collision energies to see which collision energy for the given MRM gives us the best intensity. So let me make that right now. Okay, so here are my parameters. My precursor ion is 306.4. My starting M/Z and ending M/Z for the product ion scan is 100 to 306.4. So we won't really see a product that's greater in M/Z, I don't think, than the starting M/Z. So we'll try that. And then for the collision energy, I'll make that 20. And then I'll purge the instrument to get the pumps going, and then I'll run this. So I kept the LC time progress from our normal method. So bifenazate normally, as a target, it elutes at 2 minutes or 2.8 minutes. So I'm expecting the deuterated bifenazate to elute around the same time. Okay, so I'm actually going to do 2 scans. The first I'm going to do at 40 collision energy, and then the other one I'm going to do at 20 collision energy. This first one, let's see if anything shows up above 300 M/Z as a product, but I don't think it will. And then we'll see also like the relative intensities of any fragments at 40 versus 20 volts for the collision energy. So I just purged the instrument and I'm going to run that right now. So I just finished the product ion scan. So when I open up that data file in post-run analysis, my compound table is still my normal compound table for just standard client analysis. So I'm going to go over here to create compound table wizard, integration of TIC next, 2 processed peaks next, next, and next, next. Okay, so now my compound table should be updated with just the 2 peaks corresponding to the product ion scans that I told the instrument to look for. So after I've edited, I go to view, and then the software integrates those peaks. So it looks like this is our bifenazate. And I'm gonna just take a look at this and see what I find. Okay, so what I'm looking at for this first event is the 40 volt collision energy, and I had scanned the entire range of M over Z from 100 to 1000, but as I had mentioned, I don't think anything was going to show up that has a greater M over Z than the parent ion, so I'm gonna just change the window to look just here so we could see a little easier. So now the scale here on the horizontal axis for both event 1 and event 2 are the same. So we can see with a collision energy of 20 versus a collision energy of 40, we get different product ions. And as we'd expect, with a higher collision energy, we're going to get smaller fragments, compared to with less collision energy, we might get larger fragments. So now we can just decide which fragments we want to look for, and then we'll run the collision energy scan to see at what collision energy do we get the highest intensity of the product ions. So the two biggest peaks that I'm gonna choose as my product ion is gonna be 175.15 and 203.15 M over Z. So now I'll set up the collision energy range and I'll show you what that looks like. Alright, so I set up all of these event channels looking for the same precursor and product. The only difference for each of these channels is the collision energy, and I just brought it up by 1 volt, I guess, from 5 all the way up to 30. So then we'll be able to see, given the area of these MRM transitions at each collision energy level, I'll be able to make a graph and see which collision energy gives me the highest intensity for this MRM and this MRM. Okay, so I'm going to create another compound table based on the collision energy channels that I made. And then from there, I'll be able to copy and paste the areas for each collision energy, and then I'll graph that and show what that looks like. So when the compound table wizard creates a compound table, it doesn't put the events in order. I think it goes in order of like the highest peak or something. So I just make sure that the M over Z are the same for the first 26, because I had 26 channels, and then I'll order the events 1 through 26, and then I'll copy this and make another set for the second transition, and then I'll make sure it's ordered 1 through 26. Okay, so now in my compound table, I have the first 26 are this first transition, ordered 1 through 26, and then the second 26 are the second transition that I have, also ordered from 1 to 26, because this is going to be in order of increasing collision energy. So now I'm just going to find these areas and then copy and paste them into a spreadsheet, and I'll show you what that looks like. Okay, so here I copied the peak area for its corresponding collision energy channel, which we did from 5 to 30. So when I charted these, I see that for this first transition, either 20 or I think 20 is the max. So I'll choose collision energy 20 for this first transition, and for the second transition, I'll choose collision energy 11. And that's how I'm able to choose the best experimentally determined collision energy for this bifenazate deuterated. So I'll add that to my method. In fact, I'll write it here in the spreadsheet, and then I'll add it to my method when I add it later. Okay, here I have the collision energies noted for whenever I add bifenazate deuterated into my method. So another thing I want to show is, so I've tried this for some other analytes. So we already look for avermectin, but I wanted to find if our original method collision energy is actually the optimal collision energy, and I found that for this transition, it was not experimentally found that the original method's assigned collision energy was the most efficient, so I will be changing that to our experimentally determined highest intensity given this test for collision energy. And then the other thing that I did is I tested the collision energies in different matrices. I did the collision energy test neat without any matrix, and then I also did it with cannabis flower and cannabis oil. And you can see like how suppressive in terms of the intensity of the area, how suppressive oil is for this analyte.